Thanks for coming. And today, most likely, we'll finish early. So for the proper lecture, I probably need half an hour. So we are inside the topic of crypto. And there's a last interesting topic called RSA algorithm. And this is one example of public key codes. So the main topic is this item. But before we do that, we need to introduce Euler's function, Euler phi function, and Euler's theorem, because this is used in the algorithm. So after that, well, we'll do some kind of revision, which I will use last semester exam as examples. Okay, so let's first finish the proper lectures. So let's start from Euler's generalization. Remember last time we stopped at Fermat's Little theorem. I'll remind you in a moment what is Fermat's Little theorem. It looks very similar to this. Okay, so that's why we have this. We call it Euler's generalization of Fermat's theorem. Okay, so the theorem says this. Given a positive integer n, right? N is 17 or n is 20 or just any positive integer. And suppose this number a and n are co-prime. Co-prime means they do not have a common factor other than 1. So a and n are co-prime. And then a to the power of this funny guy called Euler's phi function, phi of n, is congruent to 1 modulo n. So the main thing I'm going to introduce is this Euler's phi function called phi. So what is the definition of Euler's phi function? So phi of n is a number which counts the number of k so that k is between 1 and n, and k and n are co-prime. So I give you an n. You look at number from 1 to n, and then see how many numbers are having GCD with n equal 1. Right? How many numbers are there which has no common factor with n? Then you count. The result is Euler's phi function. So let's look at some examples, right? So for example, phi of 4. The claim is 2. Why? Because we look at numbers. We look at the numbers from 1 to 4, right? We look at them one by one. Now, if they have a common factor with 4, right, this is the n. If they have a common factor with 4, we cross them out. For example, here, among these 4 numbers, 2 certainly has a number that has a common factor with 4. And obviously, 4 itself has a number that has a common factor with 4. So these 2 numbers are out. So the remaining ones are 1 and 3, right? 1 and 3. So 1 and 3 are the numbers appear in this funny set. So this is 1 less than equal to k less than equal to 4, so that k and 4 are co-prime. So in this example, if you look at the set, it only contains 1 and 3. So phi of 4 will be the cardinality or the size of this set, which is 2, because it has 2 elements, right? So phi of 4 is 2. Okay. Now let's look at one more, right? Phi of 6. So we look at the numbers from 1 to 6. 1, 2, 3, 4, 5, 6. And then among these, we cross out those having a common factor with 6. For example, 2 and 6 have a common factor 2. So you cancel out 2. Now 3 and 6 also have a common factor 3. So you cross out 3. Now 4 and 6, they have a common factor of 2. So again, you cross 4. And then 6 itself always you have to cross. So the remaining set only contains 2 elements, 1 and 5. So if you count the size of the set, is again 2, right? So phi of 6 is 2 because among these numbers, only 1 and 5 are co-prime to 6, and others are be crossed out, right? So others are not. So phi of 6 is the size of this set, which is 2. Okay? So simple enough, right? Now, in general, or slightly more general, suppose phi is a prime number. What is the Euler function taking this prime? What is the value? Well, the claim is p minus 1, right? Because if p is a prime, and then among these, among the numbers less than or equal to p, only p itself are crossed out. All the first p minus 1 elements are there. So therefore, if you count how many are there, you get p minus 1, right? So let's just try say my favorite prime number is 7. Okay, so let's say p is 7. So you look at 1, 2, 3, 4, 5, 6, 7. Well, among these numbers, only 7 has a common factor with 7 because, well, that's a menial prime. So if you are prime, anything less than you cannot divide you, right? So therefore, the phi of 7 is obviously 6, which is 7 minus 1, right? So this is the item 3 says. Okay, phi of a prime is prime minus 1. Now, here's the statement of Fermat theorem. The Fermat's-Little theorem says, if A and P are co-prime, then A to the P minus 1 is congruent to 1 modulo P. Now, look at this form, right? This is exactly a special case of Euler, right? Because Euler theorem says, if A and N, now think of N as P. If A and P are co-prime, and then A to the power of phi of P will be congruent to 1 modulo P. But we just observed phi of P is P minus 1. So therefore, Fermat's theorem is a special case of Euler's theorem. Right? So Euler's theorem, in other words, Euler's theorem is a generalization of Fermat's theorem. Actually, historically, I think Fermat has the habit of not writing the proofs. So he writes fantastic claims without proof. Usually, is people later people prove Fermat's theorem. So the first proof of Fermat's little theorem, somebody says Euler. Euler gives the first proof. Anyway, so here's the so Fermat's theorem is a special case of Euler's theorem. Okay, so now we want to stay a little bit longer at Euler's phi function, right? So that we get some feeling. Okay, so let's look at. We see some examples of calculating phi. Now, is there a general formula or general algorithm which calculates the phi function? The answer is yes. Now, before we proceed, let's look at a special case. We are going to use only this special case. Okay, so let's look at a special case where the n is a product of 2 distinct primes, like 2 times 7 or 7 times 11. So n is something like this. So n is a product of two distinct primes. Okay. So let's calculate what is phi of n. Okay. So we use inclusion-exclusion principle, right? So we have to cross out all the guys where the guy has a common factor with n. So we use inclusion-exclusion principle to calculate out who do we cancel out, and then we use the number n minus of that number. We get phi of n. Okay. So let's see. So who are the guys we are going to cancel? So let x sub p denote the number k between 1 and n, right? P times q is n. Between 1 and n, such that k has a common factor with p, right? Now, so it is because p is a prime, that means p divides k. Okay. So the xp denotes the number between 1 and n, so that n and k has a factor of p. Okay, so it's easy to see that the size of xp is q. Right? Altogether, you have p times q many elements, and then you just divide by p, you get q. Right? So this is a size of x sub p. Similarly, you look at the number between 1 and n, such that it has a common factor with q. In other words, q divides k. You get the size of xq equal p. Right? The same reason, because every q numbers has a common factor q, right? So you just cancel out q, 2q, 3q, and so all the way to pq, right? So you get this. Okay, now let's look at inclusion-exclusion principle. So the size of xp union xq will be this, right? Now x sub p is q. I should swap the order, but x sub p is q, xq is p. Now the intersection is a number which is a multiple of both p and q. But we are looking at numbers between 1 and pq, so there's only one number, which is n itself. So just take away the 1. Okay? Sorry, there's a typo. The size of this is 1. The intersection is the n. Sorry, I'll change it later. Okay. So what is phi of pq? So these numbers are the guys we are going to cancel. We are going to cross, right? Because these guys have common factors with n. So the total the numbers remaining in the set is what we want to count, right? Phi of pq will be the total number, which is pq, minus these numbers, right? So these, okay, so it's pq minus p, okay. So then you can factorize it. It turns out to be p minus 1 times q minus 1. And then you can, for those who know some number theory, you know that in general the form looks quite close to this. Okay. Okay. Other than this typo, I hope it is clear. Okay. All right. So now, what is a general? How to calculate Euler's function in general? So here's the general way of calculating. So first, you have to generalize the proof we had to m and n, where m and n has no factor. Just now we have p and q. Obviously, if p and q are distinct primes, they have no common factor. So you have to generalize the fact to arbitrary m and n. It's not hard to show this, but okay, this is general education module, so I will not prove it. So you can find it on internet or whatever. So there are several proofs of this. Okay, so let's take this for granted. So if m and n are co-prime, and then phi of the product is the product of phi. Right? Phi of mn is phi m times phi n. suppose we believe this fact, we take it for granted, then we'll have this. If you ask me to calculate phi of n, right? So the first step is I will factorize n into this form. This we have seen it several times, right? For any natural number, you can factorize them until C prime. Factorize them into a product of primes. So any natural number, you can write it in this way. P1 to the K1, dot, 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 to Pm to the Km, where the Pi's are prime numbers. Okay? So then apply this fact. So phi of n will be phi of this bunch of product. But phi has this nice property. If they don't have common factor, you can break them and apply phi to each of them. Now these are distinct primes, so they have no common factor. So you can break phi n into phi of this guy and phi of that guy, right? So you reduce the task of calculating phi of n into calculating phi of a prime to certain power. But the phi of a prime to certain power is easy, because below phi to the k, the only number having a common factor with n is p, how to say? Because this is p to the n, so if you have a common factor with p to the n, you must be divisible by p, right? So therefore, all you need is to calculate, you take away the multiples of p. But multiples of p less than p to the k is p to the k minus 1. Is it trivial or? Okay, since I don't want to prove these, I want to skip all the proofs. So you can see it's not hard. Okay. So you get this. Now, therefore, you can calculate phi of n by following these steps, right? Because this item will tell you how to calculate the component on the right-hand side of this. Now, after you calculate each component, you multiply them together, so you get phi of n. Okay? So there's a method to calculate phi of n in general. You look at you factorize them, and then apply phi to each prime factor, and then you multiply them together. Okay, so that's the way. All right, so let's prove Euler's theorem for a special case when n is pq. Again, all proofs are optional, so you don't need to write it on your help sheet. Okay, so let's see. So I want to show Euler's theorem for this special case when n is p times q. Okay, so what is the statement? So the statement says if A is not divisible by p or q. Just now it says if A is co-prime with n, but n only have factor p and q. So this is the same as A is co-prime with n, right? If A and n has a common factor, it's either p or q, because n only has p and q as factor, right? So this is a translation of A and n are co-prime. Now Euler's result says this: then A to the phi of n is congruent to 1 modulo n, right? So phi of n, just now we calculate phi of n, phi of pq is p minus 1 times q minus 1, right? So this is phi of n. This is the value of phi of p times q. So we want to show A to the power of p minus 1 times q minus 1 congruent to 1 modulo this pq. Okay? So in other words, remember the definition of this congruence. It means the difference is divisible by pq. It's a multiple of p times q. Right? So in other words, we want to show that p times q divides the difference of these two guys. So the p times q will divide. This vertical stroke means divide. So p and q divides this guy minus 1. Right. This is what we want to show. This is what I want to convince you. Okay, so now since here I need to use a small fact about numbers. So since P and Q are distinct primes, I want to show their product divide this. I only need to show each individual of them divide the number. So here I use a small fact about natural numbers. So I only need to convince you that if P and Q are, if P divides this number, Q divides this number, and PQ are primes, then P times Q divide the number. Okay, so now I want to convince you this and that. P divides this funny number, Q divides this funny number. Okay? Now, let's apply Fermat's little theorem. So, A has no common factor with P and Q. So A and P are co-prime. So we can apply Fermat's little theorem to P, right? So we get A to the power P minus 1 is congruent to 1 modulo P, right? Now if you have A to the power something modulo 1, that is very nice, right? We can raise more powers. It's still congruent to 1. So let's raise both sides Q minus 1 power. So we get this is still congruent to 1 to the Q minus 1 power. But the number 1, no matter how many power you raise, remains 1, right? So therefore, you get the right-hand side is 1. So you get this guy congruent to 1 modulo P. Let's translate back to our, unravel the definition of congruence. It means the difference is divisible by P, right? It means the difference is multiple P. In other words, P divides this number. Now, similarly, the same argument, right? Just change P to Q, you get this. Right? You get Q also have the same thing. Because by little Fermat, you get A to the Q minus 1. Modulo Q is 1. And then you raise it another P minus 1 power, you get the same thing. So it's exactly the same proof. So P divides this funny number, Q divides this funny number, so PQ divides this funny number, and then we are done. Okay, so, well, this is a proof of the special case. All right, so let's look at the example. So the example, so we want to find a number x such that x is between 0 and 15. And so x is a remainder, probably you can think of x is a remainder of this funny number, 1 divided by 15. Okay? The question is, okay, so there are two remarks, right? So why do we care about this? In a moment you'll see that in the RSA algorithm, we care. So this we do care about this. The other thing is, here we need an Euler theorem because 15 is not a prime. So Fermat, little Fermat does not help directly, right? So here Euler theorem is indeed useful. Okay, right? So let's look at this example. So we want to find an x which is a remainder of 15 divide this funny number, 17 to whatever. This is obviously not important, right? 2019 because this. Okay, so let's use Euler's theorem. So calculate phi of 15, right? So this is, so phi of PQ is P minus 1 times Q minus 1, right? Now 15 is 3 times 5, so it's P is 3, Q is 5. So this is 2 times P minus 1 times Q minus 1. So it's 3 minus 1 times 5 minus 1. So it's 2 times 4. So it's 8. Right? Okay, since 17 is a prime number, 17 and 15 are co-prime, we have this number to the phi of 15 is congruent to 1 modulo 15. Right? So the the purpose of little Fermat or Euler is to get some power congruent to 1. As soon as we get some power is congruent to 1, it's very easy to handle other powers. Right? So once you have this, this is the base, you continue to get other results. So therefore, so x is congruent to this number. Wait, how come I jump to here? So you have to use 8 to divide this funny number to get the remainder. I think I missed something. So raised to the, so what is the remainder? Okay, so you have to this raised to certain power. So this, suppose divide by 8. So this is, suppose this is q times 8. I believe it's plus 3. So this will be the q. So you raise, you calculate this number. So let us calculate. So this is 2, then 41, right? 2, 5, 2, 5, 2, right? 2, then you get 16, right? Okay, so this is 2, 5, 2. Sorry, there's so many typos. So this is 2, 5, 2. And then remainder is 3. So sorry, q is 2, 5, 2. So the remainder is 3. So now once you know 17 to the power 8 is congruent to 1, the thing in the right bracket suddenly become 1. So it's congruent to 17 to the power 3. Now congruent to 15, well, 17 is congruent to 2, right? Because 17 is 15 plus 2. So actually, this is congruent to 2 to the 3, 2 cubed, but that's 8. Right? So it's not hard to calculate. Yeah, sorry for the typo. Okay, so that's the Euler theorem and one tiny application. Okay. So this is our main topic today. So we are going to introduce a very interesting coding system, right? So and supposedly it's safe. Okay, so here. So remember that, okay, so we are talking about crypto systems, right? So last time we introduced this affine transformation. So what you do is you look at a linear transformation, right? Remember that you look at f of x is ax plus b, right? So you have, for example, you want to do modulo 26, right? So you choose AB, this will be the key, right? So you do something, so I give you a letter, you change the letter into some number, and then you calculate f of that number, modulo 26. That is the message you send to the other party, right? So those are, these are the old or traditional crypto systems. So for example, the alpha transformation is something like this. So it depends on a common key for both enciphering and deciphering, right? So the pair AB is important. It is important both for me, which I code the message, and for you decode the message, right? So this is so the common key. It stands for this key AB. So now this slide is trying to say that there are some problems. This is not very good. There are some disadvantages. Okay, so the security depends on the ability to keep the key safe in two places, in the sender and the receiver. So also you need to pass the key from one side to the other side. So there's lots of problem because the more action you need, it's possible the information was out and people can get the key and see your message. Okay, so now in the remaining 15 minutes, we'll look at things in a different way. We'll introduce a completely different system. So this is called a public key codes, and RSA is a three people's name. You are going to see them. So we are going to introduce a new kind of coding or new crypto system, which is called public. It belongs to public key codes, right? Okay, so a public key code is a crypto system in which the enciphering key is not the same as the deciphering key. So there are two keys. Okay. So the enciphering key may be made public. Only the receiver has the deciphering key. Okay. So ability to encipher does not enable you to decipher. So what does it mean? Okay, so suppose I want to get some feedback. So I create a pair. I mean, I create enciphering key and deciphering key. I hold the deciphering key. I will not tell anybody, but I can tell the whole class about the enciphering key. Okay. So I hold, let's call the enciphering key E and deciphering key D. I hold D and announce E to the whole class. So anybody want to send me a message, use E to, you are going to see how they do it. So use the E. E is public. Use the E as a tool to code some message and send to me. Okay. Now, besides me, supposedly nobody will decode the message. Even you know E, as long as you don't know D, it's almost impossible to get the original message. So he says that, for example, he sent me a message using E, right? So the thing was public. And people see his message. But as long as you don't know D, right? If all of you know E, right, you cannot decode the message. So I can see the individual message because I have D, so I can decode it. Right? So we are going to see the example like that. Okay. Okay. So what is RSA? So the most famous public key code is so-called RSA crypto system, invented by, this is R, S, and A. And the picture, the resolution is not too good, so these three people. And there's a name Turing here, so because they won the Turing Award, which is the best award in computer science. So because of this. I don't know whether it's true or not, but some people say in some secret service they already know this this coding, but because they are nature or because they are secret service, so they cannot publish, and so those clever people working in the wrong department somehow didn't get it. Right. So anyway, so this is an interesting. So let's see the procedure. Okay. It's hard to believe, right? This is clever. So I can give you a number, and you use the number. You can send me a message. Other than me, nobody can decode it. So it's very sounds very strange, right? Okay. Anyway, let's see how it was done. It's fun, and the method was so simple that I can teach in a general education module. It's extremely simple. Okay, you'll see. Okay. Okay, so let's see the procedure, how this was done. Okay, so first you have to pick two large prime numbers, P and Q. Okay, so how large is it? So in practice, each has about 200 digits. This is extremely large, 200 digits primes. And now you calculate their product. So this is capital N. is the product of these two gigantic prime numbers. Okay. Now pick any integer e that is co-prime to that's why you introduce Euler's function, right? So pick any integer e that is co-prime to this phi n, which is p minus 1 times q minus 1. Okay? So this e will be the encryption key. Okay? So, and then I determine multiplicative inverse d of e modulo this phi n. Right? Because e is co-prime for this, so there is a multiplicative inverse. You have tutorials and you have tried this. Right? So in other words, d times e is congruent to 1 modulo this phi n. Okay? And d will be the decryption key. Okay? So these 3 steps was done by me. Okay? I choose 2 large prime numbers, p and q. I multiply them together, and then I choose a e which is co-prime to this, and then I solve this equation using Euclidean or whatever, using the method. I get d. So I did this. Okay, 1, 2, 3. So now I publish the pair n and e. So I'll send n and e in the lecture, right? Including those watching webcasts, they all see the n and e. Okay, so they all see these 2 numbers, but they don't know these. Even if they know this, then no secret at all. So they only know n, they don't know these. There's an interesting question, right? Because n is p times q. If you know n, how hard is to get p and q? Well, you'll see the answer in a moment. Okay. So are you with me for this? So the procedure is I prepare some number, right? I prepare PQ capital N E D, right? I do these. And then I publish the capital N and E. Essentially I keep D. D is the thing I keep. Okay. So now how do you send me the message? Okay. So you send me a message, you represent the message you want to send to me as a number. Well, we always do that. So the number is less than, say, between 0 and n. This n will be huge because n is p times q, and p is like 200 digits. So I don't think in your, so this actually can send me a lot of things. Okay. So let's assume that you want to send me a number, this number m. Okay. Now the encryption is this. To send me a message m, right? This m you want to send me, compute the remainder of m to the e on division by n. In other words, you calculate y, which is congruent to m to the power of e. E is the key, public enciphering key. I give it to you, right? So you calculate this modulo n, right? Because you know capital N, you know e, right? And m is, again, you want to send me that message, so you know small m. So you can calculate y. You calculate y, right? Then you send. You can make it public, right? So y is the message. Okay. Now, when I receive the message y, what I'll do this. I will compute y to the power of d because I know d. I have d in my proposal. So I know d, I'll calculate y to the power of d modulo the same n. Right? This n is public, so it doesn't matter. So in the next slides, I will convince you that y to the power of d indeed is congruent to m modulo n. So if I compute y to the power of d, then I compute the remainder, right? I'll get your message m. Okay. So this part, we are going to use Euler's theorem and so on and so forth. Okay, so let's see. So here's a proof. Okay. So I want to show this, right? So you send me y, I raise it to the power of d, right? So your y is m to the e, right? M to the e. So I raise it power to the d. So the y to the d is m to the ed. So we want to show that this guy, y to the d, is congruent to m modulo n, right? Y to the d. So that if I do this arithmetic, I'll get your message small m. Okay. Now why? So because e times d is congruent to 1 modulo phi n, right? That is the way I choose the key, because I choose d to be the multiplicative inverse of e. So therefore, e times d is congruent to 1 modulo this Euler function phi n. So in other words, so the difference is a multiple of phi n, right? ed minus 1 is something times phi n. Let's say it's t times phi n. So ed minus 1 is t times phi n. In other words, e times d is t times phi n plus 1. Okay? Now, case 1. Most likely that small m and capital N are co-prime because the n only have two factors, p and q. So usually the m will be co-prime. So case 1 is indeed the small m and capital N are co-prime. This case is easy. It's a direct application of Euler theorem, right? So if m and capital N are co-prime, then m to the I think I messed up capital N and small n. So they are the same. There's only so m to the phi capital N is congruent to 1 modulo n. Okay. So therefore, y to the power of d, which is m to the e times d, and e times d is a multiple of phi n plus 1, so it's m to the phi n and this multiple, and there's plus 1, so there's a m here. So m to the ed is m to the phi n times d plus 1. So in other words, it's this guy times m, right? There are so many typos. Sorry. So this guy is 1. This guy is congruent to 1, right? Because this power is 1, but I have another m here. Sorry. This part, because of this, in the bracket is congruent to 1. So you raise it to the power d is still congruent to 1. But the m is still there. So I have to miss an m here. Okay. So therefore, y to the power d actually is congruent to m modulo n. Okay. So this is the case where we can apply Euler theorem directly. Now, what happens if m and n are not co-prime? Well, applying it still works. So it happens to be that way. So the proof is similar to what we have done before. So suppose m and n are not co-prime, then either, because n only has two factors, p and q. So either m has a factor p or m has a factor q, right? So either p divides m or q divides m, because n only have two factors. So if you want to have a common factor with n, you must have one of them, right? Okay, so let's assume, because they are symmetric, let's assume it's p divides n. The other case is similar, just change p to q. So if p divides m, and then m cannot have q as factor anymore, because if m also have q as factor, m will be bigger than n. So if m already have a factor of p, m cannot have factor q anymore. So m and q are co-prime, and then we use Fermat's theorem. It's just like what we did. So m to the q minus 1 is congruent to 1 modulo q. So y to the d is the same. I'm copying down this. So it's m to the power t times, this is phi n, right? This is phi n plus 1. So this is m to the q minus 1 to the t minus 1 times m. M again is this 1. Now, again in the bracket, this part is 1, so the whole thing is 1. And then you have an m, so we have this. Okay. So in other words, q divides yd minus m. Q divides this guy minus m, right? Now, P clearly divides this because P divides m. Here, these are all multiple of m. So if P divides m, then P divides all of these. So P divides this guy, Q divides this guy, so n will divide this guy. So therefore, if you use n to divide this, the remainder is n. Now, again, the proof is for fun. Okay, so now the question is, so you more or less know the procedure. The procedure is I do this funny calculation, and then I have a pair E and D. So I hold D, I give you E, right? And then if you want to send me a message, use E. And then after I receive, I use the D to decode your message. Only people who has this D can decode. Right? So that's the claim. Is the claim true? Okay. So why this is safe? So the enciphering key, the pair N and E is public. Anyone can use it for encryption. Right? I publish in a lecture, so any of you can use E. Now the prime factors P and Q of the capital N, so I'll unify this. Okay, so keep secret. So if they are known, then the deciphering, there's so many types. D will be, you can find D also. Okay. So our phase is based on, so the security relies on the practical impossibility of factorizing large numbers. Right? So even by the fastest computer of today. So the security relies on, if you know capital N, you cannot find PQ within 2,000 years or within 100 years. Okay. So here are some data. It's a long read, but okay, so let's see. So the most difficult integer to factorize in practice using the algorithm are those that are products of two large primes of similar size. Right? And for this reason, these are the integers used for cryptographic applications. So the largest such semi-prime, so semi-prime is a product of two primes. It's almost a prime, but no. Okay. Yet factored was something, okay, so some number. So this number, you have 232 decimal digit. Okay, so the factorization was collaboration of several research institutes spanning 2 years and taking the equivalent almost 2,000 years. So, okay, if you have not very fast computer, it takes you a lot. I mean, this probably is very fast. So like all recent factorization record, this factorization was completed with a highly optimized implementation of the general number. Okay, so there's some number theory terms run on hundreds of machines. So it's very difficult to factorize a number. So I guess, okay, so for those who are in computer science or in engineering, so you know that this is an example of so-called one-way function, right? One-way function. What does it mean? One-way function. So it is easy to calculate. So suppose you know P and Q. So this way is easy. Okay, if you know PQ, to get N is easy. Now, if you want from n to get to get P and Q, the pair. This is extremely difficult. So that's why it's called one-way function. It's easy to go one way, and the other way is not easy. Now, whether this is true or not, this is depend on the phase, right? So it could be that some clever people like you could show that actually there is a way. Right? So far, there's no theoretical proof. Actually, since this is the last lesson, so I can say some. Okay, so actually, there's a famous result recently, maybe 10 years old, or so. There are 3 Indian computer scientists, or number theorists, Manindra and 2 other people. So there are 3 Indian mathematicians. So they showed. So I don't know. I'm sorry, I don't remember the name. I only know the first house of Manindra because he visited our department. So anyway, so there is an algorithm. So there's a theorem says okay. So I write it in shorthand. Right? So this primality problem is in P. Okay. So I give you a number. I ask you whether this number is prime. In other words, whether you can have a factor of him. Right? So I give you a number. This number, I don't know, 1, 2, 3, 4, 7, 8, 9. So they will give you a very, very big number. So I ask you, is this number a prime number? Right? Now, so the question, that question is called primality, prime. So the prime stands for that question. So I give you a number. Can you give me yes or no to say, oh, it's a prime or it's not prime? Are you with me? So you know what I'm saying, right? I give you a number, so 15. That's the biggest number I can think of. Is 15 a prime? Well, you have algorithm, you use punch calculator and say, oh, 15 is 3 times 5, so it's not a prime, so you answer no, right? So now I give you, I don't know what, I give you a large number, right? 3, 3, 5, 5, 1. I don't know, so or even larger. 2 to the 2019 minus 1. I give you this number. Is it prime? Right? So the question in this form, I give you a number. You have to give me yes or no, depending on whether this is a prime. So that's a problem. Now, what they show is this problem can be solved in so-called polynomial time. So it can be solved relatively fast. So when we talk about truth tables, right? We say decide certain formula whether it's a tautology or not. This again is sometimes it's difficult because you have to do exponential. Now this is similar. So for computer science, if a problem is in polynomial time, it's considered easy. If the problem is NP hard or whatever, then it's considered difficult, right? Now this determining whether a number is a prime turns out to be easy because it has a polynomial time computable algorithm. And then you would say that, wait, if determining something is a prime is easy, is polynomial time, why RSA is safe? Right? The catch for their algorithm is they can tell you yes or no whether this number is a prime or not prime. They cannot give you a factor. They don't use the way you think. They don't check, is this a factor, is this a factor? If you check this, no hope. It's definitely difficult. And then they do some clever, they use number theoretic properties. Then they test some other properties. Then they can decide whether this number is a prime or not very quick. But even you know this guy is a prime or not prime, it doesn't give you a factor. So this is quite interesting. Anyway, so the message was to factorize. I give you a big number, capital N. to factorize n into p times q is hard. It's even this computer with very advanced technology is still hard. So that's why the RSA is safe. Okay. Well, let's look at example, and then we take a break. Okay. So let's look at example. So here, of course, we cannot choose a 200-digit prime and multiply. That's too big. So let's look at the baby version. Suppose I want to send this message. I don't know. M is 141. Right? So you use RSA to okay. You have these public key. N is this, and E is 47. Okay. So I publish these two numbers, 1273 and 47. Right? You want to send me 141. Right? So what is the number you send me? Well, this is the number you send me. So you want to send me Y. Okay, so you know M, right? So you raise M to the power E, and then calculate the remainder. Okay, is it easy to calculate? Okay, so then you have to use the thing you learned in the previous lecture. So you have to do the modulo exponentiation, right? So the trick is, okay, you write them as the power of 2s. So the congruence, each time you calculate this, you get the 141 to the power of 2s is congruent to what? Right? So you get these. So therefore, this guy to the power of 47 is a product of these guys. Now you just calculate these guys. What are the remainder? So you just multiply them and then do some calculation. In the end, it's this number, okay, 658. Please check, right? I don't have any confidence of these. I took it from book. So. But the method is clear, right? So you want to send me you want to send me 141, right? All you need to do is to raise this to the power of E and calculate remainder. And somehow the remainder is this. Send me this. Okay. So people who do not know the pair, the D, will not. It doesn't know it's 141. They see 658. They have no idea what it is. So that's the encryption part. Let's look at the decryption. So suppose we use the RSA. So we receive this number 1252. Right? So we want to know what it is. Right? So the public key is this. Okay. Now we have to assume. Okay. I have to know how to factorize, right? Because the person who designed the system knows the factorization. So you have to assume that this n is factorized in this way. Okay. So the solution is, so we have to design the key, right? So we know the factorization. So we can calculate the Euler function of this guy in this way, and then we find the multiplicative inverse of 47 modulo this number. Okay, so this number is 1,000 this. So in other words, you want to find 47 times, actually I should change it to D. So D times D is congruent to 1 modulo this. So you do this Euclidean algorithm, and okay, so you do these funny things, you find the multiplicative inverse. So in the end, it's 31. Now, once you have 31, you can decode the message. Right? I receive this number 1252, so I raise it to power 31, and then divide by the capital N. Right? So again, we use modulo exponentiation with all the congruences modulo this capital N. Okay, you do this business to raise to the power 2 and get it. So the plain text is 125. Okay, so that's the how it works. Okay. So it's easy enough, right? So, and somehow this is an amazing result, and people get Turing Award for designing this. It's quite interesting. Okay, so the last remark is maybe you want to send a very long message. So the way is you chop off them into blocks and then send each block. But this is probably well, for us it's not important. Right? So we just want to know how RSA was done. Whether in practice how it was done, only engineering or double E people can. Okay, anyway, so I think that's the last slide, right? So now let's take a break, and feel free to leave, because I'm going to explain the last semester to the exam questions. So I suggest you try it, right? So if you don't want to do it, you haven't done it, probably it's not good to listen. Because I think it's recorded, so or I upload the notes, you can read it anytime. So I suggest you try it yourself. And but if you want to listen, I'm fine. If everybody leave, I will stop. Okay, so let's take a break and see how it goes. Okay, so let's continue. So these questions I already upload. So these are taken from Professor Canvey test exam. Okay, if you spot any mistakes of the solution, talk to me. It's mine. Okay, so today I'll probably talk half of them, give you a chance to try more. Okay, so question 1. So here's a question. The following is a correct argument. So it means logically sound or valid. So the argument says this. All roses are flowers. Some flowers fade quickly. Hence, some roses fade quickly. Is this a reasonable or good argument? Okay, so the answer is false. So this is not valid. For example, so I think draw a diagram is easier. So here is flowers. Right? So this is all flowers. So all roses are flowers. So the roses are inside flowers. Now inside the flowers, there are some flowers are fade quickly. So maybe those fade quickly are here, right? I don't know, quickly, Q. Okay, so the shaded part are faded quickly. Now in this case, we cannot conclude that roses fade quickly, right? So therefore, logically, this is not. Please don't treat this as a biological question. Right? I don't know in real life whether probably some roses does fade quickly. And so the question is about whether this kind of argument is logically sound. It's not about the biological fact whether roses fade quickly or not. Right? So let's. Now logically, maybe you can do, if you want to be more mathematical, right? So this, I give an example, say, like I draw over there, or I use example, say, maybe some flowers are orchids. Right? Orchids, is disjoint from roses, I believe. I don't know. Okay, so orchids fading quickly has nothing to do with roses. Right? It's like the part we draw. But if here are the orchids, so orchids is destroying from roses. So this part faded quickly doesn't have nothing to do with R. Right? So therefore, or you can use more logical. Okay. Anyway, so is this okay? You understand? Right? Okay. Now question 2. So the following two sentences are logically equivalent. So this is testing you whether you understand the meaning of logical equivalent. So what do we learn? We draw a truth table. If the truth table are the same, then they are logically equivalent, right? But I guess if you draw a truth table, it's false. Let's try, right? So I claim that when P is F, Q is T, R is F. Okay, let's see. Let's calculate, right? So if I give P F, Q T, R F. So what do I get? So P arrow Q will be true. So it's true arrow F. So this is F, right? So the first statement is false. Okay. The second statement, okay, P is true. P is false. Q is true. So P and Q is, this is false, right? Now R is false. So first arrow false, so this will be true. Right, so the second, so this formula turns out to be true, this formula turns out to be F. Right, so therefore they are not equivalent. Equivalent means if I give you the same input, you must give me the same output. But now I give you the same input, F, T, F. The first one turns out to be F, the second one turns out to be T. So therefore, they are not logically equivalent. Okay, so the safest method is draw a truth table. I think you can. Then you don't need to think. You just draw it and then you see. Okay, so question 3. Okay, questions 3 and 4 concerns the following setup. So F is from X to Y, G is from Y to Z. These are two functions, right? The composite of the two functions is a function denoted in this way. G circle F is a function from X to Z, defined by you first follow F, and you follow G. Right? So I guess you have seen this kind of diagram many times. So this is X, this is Y, this is Z. So F is from X to Y, and G is from Y to Z, right? So now you want to calculate the so-called composite. So the composite is a function from the first, the domain is the first region, and then the codomain is the Z, is here, okay? So so the definition is clear, right? So the composite will be, you follow this arrow. For example, this point, follow F of X, will send you to here. And then you follow G, will send you there. So the value of F of X, this funny thing of X is this, right? So this is the setup. Okay. So now the question is this correct? Question 3 says, if F is injective and G is surjective, and then this funny function is surjective. Okay, so it tells you whether you understand injective or surjective, right? So what is injective? Different points send to different points. Right? This is injective. Surjective is you hit everybody in the codomain, then it's surjective. So, is this true or false? So I say this is false. For example, you can find examples, right? For example, if I choose my x, okay, so here's the example. So I'll draw the graph. So I take x to be 1, y and z to be 1, 2, okay? And f is just send 1 to 1. This is certainly injective. And g is, okay, so this is surjective from x to z, from y to z. But if you look at this from x to z, x only have one element, z has two elements, so it's impossible, right? So the picture is, I have x only has one element, which is 1. Now I have y, okay, so I have one dot here, I have two dots. One is 1, one is 2. And z is 1 here, 2 there, right? So this is my f, and this is my g. So f from x to y is injective. There's only one arrow. So now g certainly match everything here, hit every point here. Z only have 1, 2, right? So gy is 1, g2 is 2. So g is surjective. But if you look at the composite, it has only this. So it does not hit everybody in Z. So therefore it's not surjective, right? So it's quite easy to see. Okay? How about this? If the funny guy is injective, then G has to be injective. So the answer turns out, okay, claim is false. So for example, more or less the same. Right? So take x to be 1, y and z to be 1 and 2. So f is the same, and g, I want g to fail to be injective. Right? G will send everybody to 1. And then g is not injective, but the composite is injective. Right? So the picture is like this. So this time let me draw larger. So this is my x. It only contains one number 1. Okay. So this is my y. So I have 1 and 2. And z here, this is only have 2 points, 1 and 2, right? So f is just this function. This is my f. Now g, I want g to be not 1 to 1. So this is my g. So g is not 1 to 1. No, not injective. 1 to 1 is another name for injective. Right? So because I have 2 points sent to the same point. So G is not injective. But look at the composite. G is so-called F. It's just send this point to that point. So it's injective. Right? It's just. Now you can have lots of other examples. So, but this is it's easy to see. Okay, so question 5. Gödel was the first to prove that there's no bijection between sets of integers and the sets of real numbers. So this is a historical, test your historical facts, right? And we talked about this before, right? So we also covered this. So the answer is false. So here is no argument because historically, Cantor is the first person to show this. Remember we did this diagonal argument, right? And then some student after class when we talked, right? So it is Cantor. Cantor is the father of set theory. Right? He invented the diagonal method to show that real number is uncountable. So that's the result. Gödel is famous for showing the so-called incompleteness theorem. Right? So we mentioned it, but we are unable to make it exact because it's too involved. Okay, so this question is there's no Okay, now the next 3 questions, they are about voting. So this is, we learned these 2. Okay, so here's the setting. So from question 6 to 8, consider the following voting profile. Profile means this, right? For an election with 4 candidates A, B, C, D. Okay, so the number of votes are like this, and the rank. So 2 people rank A first, C second, D third, and B third, C, D fourth, right? And so on and so forth. Okay, so question 6 says there is a Condorcet winner in the above election. Do you still remember what is Condorcet winner? So this guy would beat everybody head to head, right? So if you have a person who beat everyone, right, then he's a Condorcet winner. Is it? Okay, so let's try. So according to this ballot, this profile, help me. Maybe I made mistakes. So let's see. So I think B wins. Is it true? So let's say B against A, right? How many people put A above B? So here you have 2 people. Here you have 4 people, right? So you have 6. All the others, B is above A. So altogether, let's see. So we have 18 people, right? So here you have 10 people. Here you add, you get 18. So if 6 goes to A above B, then the other 12 will be B above A, right? So B is going to win against A. Now is B going to win against C? So let's help me check, right? So who put B above C? Let's do that. Is it 10? So B. So here I get 4. Here I get 4. 1. 5. Here I get 2. 7. Here I get 3. Okay, no. What I'm counting, sorry. B above C, right? B above C. So here I get 4. Here I get 3. 7. Here I get 1. 8. 8, right? Oh, then it's wrong, right? B above C. So let's try again. So if this is wrong, then it's not, B is not Condorcet. Let's try. You are better than me, right? Try. So how many people put B above C? So 4 people here, 3 people here, 7, and this is 8. Oh no, so this is wrong. So maybe C is a winner. Right? Maybe, okay, so maybe B is not. Let's try the other. So I guess I made a mistake, right? So okay, so let's see. So B is not. So maybe C. Let's see. C, can C beat A? C, 3 votes here. 4, 6, another 6, 12. So C will beat A. C will beat B. Is C going to beat B? Hopefully yes. And then C is a Condorcet. Okay, so can C beat D? 2 votes here. 3, 5, good. 8? No, 8. So D beats C. Is it true? D beats C. Okay, so then the chance will be D. Let's see. So can D beat A? Sorry, this is totally wrong. So D, 3, 2, 3, good, 11, right? So D would beat A. B already beats C. So let's see D and B. 3, 4. Okay, wait, D beat B, right? Let's see. So how many people put D above? So then there's no Condorcet winner. Okay, sorry. So I'll change it. So this is no. Okay. Okay, so now I'll change the numbers accordingly. Okay. Okay, so this is the, but the way is you just count the head-to-head votes, and then if one person beat everybody else, that's a Condorcet limit. Okay. Now let's look at the other one. So, using the system of border count, candidate B is ranked first. Okay. So, what is border count? So you assign scores to A, B, C, D, right? If they get rank 1, they get 1 point. If they get rank 2, they get 2 points, and so on and so forth. So you add the scores. The person who gets the least score is the winner, right? So remember the system. Well, okay, don't trust me these, right? You have to help me. So let's see. So let's first calculate the border score of A, B, C, D. Okay, so well, you have to help me. So maybe some of you calculate A, some of you calculate B. Just help me, right? Yeah, you need to do a little bit of arithmetic. Probably you can help me. So A is 6 plus here I get 3, 9, and I get 11 at 4, so 44 plus 9. So I think A is correct. Right? A is correct, right? Okay, okay. Is A correct? Let's calculate B. So I get 4 votes for here, and then I have 7 times 2, 14, this is 18, and then I have 7, 21. 18 plus 21. I think B is correct, right? B is 39. Yes. C? Okay, so maybe you can help me to calculate C and D. So let's try C. 5. This is 6, right? So it's 12, 17. This is 9, right? 26, 26. This is 4 times 4, 16. Seems all right, right? C is all right. D, is this right? Wait for your result, right? Help me calculate D. Is this right? Yes? Anybody else? Is this right? Okay, if the calculation here is right, then B is a winner. Okay, so B is winner. Okay. Right, so okay, so let's move on to the next question. So question A says, now among the voting system, plurality border count, sequential pairizing voting, and higher system, there is one under which A is a winner, and there is one under which A is ranked last. Okay. Actually, for some system, it doesn't make sense of who is ranking last. So some, okay, but we can probably still answer this question. So we have several systems here. So all we need to know whether there's one under one system A is winner, under one system A is ranked last. So I think just now, if the calculation, if these numbers are correct, A ranked last under this border system, right? Border count. So all we need is whether we can find a winner under, we can find a system under which A is a winner. Is it true? So let's see. So I claim under popular plurality voting, A wins. Is hopefully right. So A gets 6 votes here, B gets 4, C gets 5, D gets 3. Okay, luckily A wins under plurality, right? So under plurality, A is the first, and under the border counting, the A is the last, long stops. These two are actually, the information is not complete. For the sequential pairwise voting, you need the agenda, you need the order. So it's very, I mean, without specifying order, it's hard to rank the candidates. So, but we don't need this. Okay. And higher system also, as long as we find the answer, we are happy. Right? So the answer for this is true. Okay. Let's move on, right? Next one. So here, this is interesting. So the system of voting, known as this SPV, sequential pairizing voting, satisfies the property of monotonicity, but the higher system of voting does not satisfy monotonicity. Okay. So monotonicity is a property of the voting method, right? So we are saying these two. Okay, one satisfies monotonicity, the other one fails. Right? I think it turns out to be true. There is an example of the higher system does not satisfy monotonicity. Okay, so if you look at lecture notes, there is an example there. So I will not repeat the example. So the higher system fails. Now, we didn't cover, we didn't show that SPV satisfies monotonicity. But we can do it now, right? So we didn't do it during the class. Let's spend 3 minutes to do it now. So this is also a good opportunity for me to formally define what is monotonicity. I think when I talk about this, I introduce monotonicity for the two candidates voting. And then I wave my hands, say, for 3 and more candidates is similar. But it turns out, well, it is true, it's similar, but it turns out that's not a good definition. To have a good definition, workable definition, we have to make it a little bit more precise. So here's the precise definition. So the definition for monotonicity for 3 and more candidates. So a method is monotone if the following condition holds. So let's use a long condition. Let's read it one by one. So it's like before and after, right? If before something happens, and after you do something, then something happens. Then it is monotone, right? Okay, so before, the condition is this. So suppose under a certain profile that some candidate A wins, right? So this is before. Before it wins, he wins. And that some voter V put a different candidate, say B, immediately ahead of A on her preference list. So suppose in the first election, right, when A wins, this voter V puts a different candidate B immediately above A. So this voter V's profile looks like this. A is here, B is there. There are lots of other profiles, other ballots, but on B's ticket, you have this situation. This voter V put B above, immediately ahead of A. Okay, right? So this is the setup. Now, that's before, right? Now, what is the change? The change is this. Imagine a second profile that is identical to the first, except the voter V moves A1 up place and moves B down one place on her preference list. So in the second election, the same voter V just swapped A and B. Okay? I hope so before is this, is B above A at voter V's ticket. After is A above B. Okay, so that's the change. Okay. So the voter V moves A up one place and moves B down. So they swap A and B on her preference list. So this is after. Right? After this, the method must still declare A to be winner when facing the second program. So if the voting system satisfies these, is monotone. Right? During the lecture I said, so that the spirit is, if you give more favor to the winner, it won't change the result. If you, especially like if you have two candidates, right? If you give some the ticket from the loser, transfer some ticket from loser to the winner, then the winner is still winner, right? So if the method satisfies that, it's monotone. But here we don't have a clear divide of winner and loser, so the definition is this. Okay. The nice thing about definition is he break up the complicated cases into just one voter, just one case. Because if you can actually we can iterate this. If several voters, they all change, they all do this change, the result won't change. And also here you only move A up one place. If you iterate this, you can actually move up A several places, because if the system is monotone, you swap one place, the result won't change. Swap another, it still won't change, right? So but the definition was easier to check because it's just zoom into this particular case, and then it's easier to check. Are you with me for this? The monotonicity means this. Before you have a ticket like B is above A, and A is still a winner. Right? After you move A up on the ticket, you must declare A also as a winner. Right? If it's monotone, it has this problem. It satisfies this definition. Okay, so now let's apply this criterion to this SPV. Right. So before I have a V, I have a ticket, A is above B, B is above A. Now after A is above B, right? I want to show you in the same system A is still winner. Okay, so let's try. So now let's argue that SPV satisfies the property of monotonicity. Right? For the sequential pairwise voting is you have to set an order, right? So then the candidates will fight each other, and then the winner progress to the next one. The loser is out, right? So suppose suppose we have this ordering. Suppose in the before the change, A is a winner. A is somewhere, right? In general, let's say A is between here. So there are a bunch of guys before him, bunch of guys after him. Right? This is the most general case. So suppose A was a winner under this agenda, following this SPV. Okay. Now this voter V changed her vote as described before. Right? Change the vote by putting A above B. Before is B above A. Now she changed. Okay. Now I want to convince you, after the change, A will still win, following this order. Right? So because the definition is so clear, it's easy to see now. Because you only change A and B. All the other position, the relative position for other candidates is not changed. Right? Suppose before C is above D, and then after C is still above D. Right? You only swap one position, the pair A and B. You didn't change anything else. So therefore, since we have that nice property, and then when B1 is played against B2, before whoever wins after is still wins, because the relative position didn't change. So therefore, if you follow this order, after the change, you get exactly the same results, right? It is still the guy who is going to fight with A. Okay, but so A would still face the same opponent, and A would win against him, right? Because now A gets even possibly one more vote, so A would still win, right? Now for the rest, if before A wins against these guys, now after the change of A is A get one more vote, so A would win even easier, right? So A would win against the rest also. So therefore, the SPV actually is momentum, right? So syncopate, right? But this is okay. So we are almost finishing because I will leave some problems for on Friday. Okay, so the next question is a historical question again. So Conway and Selfridge independently discover an envy-free division scheme for 3 persons. So the answer is, I think it's true, right? So because for envy-free, Knaster probably is credited to get a proportional division of reason, but it is Selfridge and Conway independently get this envy-free division for 3 persons. Right? So this is a historical fact. The last, I think this is the last slide I'm going to do. So according to the Benford law, the probability of 5 being the leading digit of a long list of positive integers or whatever is this. Well, we covered Benford law, but we didn't emphasize, right? Okay, so what is Benford law? So Benford law says this: the probability of D being the leading digit is this. I did put this on the slide, so but I think when I talk Benford law, I talk as a fun fact, right? I didn't have any exercise. Anyway, so in the last semester, there's a test problem like this. So the Benford law says the probability of D being the leading digit is this. Okay, so now D is 5. So you have to calculate log 10 of this number. And you have calculator, so you part your calculator. I think the result will be this. It's not that. That is probably 4. Is the but anyway, so this is false. Okay, so I guess no more, right? So for the remaining problems, we'll do it on Friday. So I suggest you to try it, right? Otherwise, we waste all these problems. Right? So you try it first, and on Friday we'll see the other answers. Okay, so see you on Friday.